Alright, before we begin our calculations, we're going to use this list of constants and equations. First, g, which is negative 9.8 meters a second squared, is your gravity constant. That'll be used in the equation change in y is equal to vertical velocity times time minus 1/2 gravity times squared. Second formula we'll be using is the distance formula, which is change in x is equal to velocity times time, which will tell you the distance. Also, in one problem, there will be a unit called a mil. And a mil is basically 0.053 parts of a circle. It's a degree count. So, if you were to raise 1 mil on the scope, you could consider that being 0.053 degrees raised. And that can be used when you're trying to fire at angles to find basically things like time and velocity on target. So think of it as 360 degrees basically if you're shooting, but every time you raise those dots, that's what that counts for. And in the video we'll be using two different weapons, the M95, which its muzzle velocity, which means the rate at which the bullet is leaving the end of the barrel, it is 854 meters a second, and the M24, which has a muzzle velocity of 798 meters a second because of its lighter payload, which is the 7.62 versus the large 50 caliber bullet of the M95. Alright, for our first shot, the target is 30 meters away. We're using the M95 rifle. So, we're going to use the distance equation, which is basically velocity times time yielding the distance. We already know the distance being at 30 meters, and we know that the initial muzzle velocity of the 50 caliber is 854 meters a second. So basically we divide 30 by 854, and we get the time to come out as 0.3 seconds to the target. But what's special about this case is, basically, at such close ranges, bullets do not drop. But, first of all, bullet drop is also an important factor in any of these equations, or any target shooting at longer ranges. Bullets fly straight, however though, gravity will slowly pull them down as they go farther and farther and farther. And based on how large a bullet is, we have to use different amounts of propellant to basically give greater velocities to the bullet so it can go farther. But you don't just aim the rifle directly at your target when you're shooting at farther distances like 700 meters plus. One has to correct, which means basically you aim the barrel above your target and allow gravity to pull the bullet down onto the target. So snipers will use manuals like this basically with different degree angle corrections for different ranges. And we'll see this farther on in our calculations when we use mils. But out to 1,000 meters, the corrections get pretty incredible, depending on what bullet you're using. For our second shot, the target is 205 meters away, and we're using the M24 rifle. And with this one, we have a 1 mil correction, and that is so that the shot carries farther. So, we start out, we're going to use the delta y equals velocity times time minus 1/2 gravity times squared. So we put in the angle, which is the 0.5 mil, And we know our initial velocity is 798 meters a second, but we have to break this into the horizontal and vertical components to basically find out what the time really is. So we're going to do sine of 0.05 with y over 798 to find the vertical velocity, which is 0.7 meters per second. And basically we plug that back in to the vertical component, and we find out that the time is 0.142 seconds. And the cosine would only be if we were doing comparative firing, so it doesn't really matter. But still, flying very fast and reaches the target quick. Alright, for the third shot, we're 50 meters above our target and 200 meters away using the M95 rifle. So basically, we start out knowing that it is a 14-degree change to angle down at the target. So, to start out, we're going to use the same equation as the last time, except this time we're firing down, but it's still basically the same. So we're going to do the sine of 14 y over 854, which is the initial velocity of the 50 caliber bullet, to find 206.6 to be the vertical velocity. So we plug that in, but also 50 because that is the height difference because we're up on a mountain above the target. And then we're going to use the quadratic because basically the target's at a different elevation than us, and to find it out it's a lot simpler also because it's challenging to factor that out, and quadratic works a lot better. So we found the time to be 0.243 seconds, which is a little bit longer, but barely. It's still 0.243 parts of a second. So that is how fast the bullet hits its target.